So now we're moving towards the more general stuff, and that will be the end of the chapter. The work kinetic energy theorem is the starting point always. That theorem tells you that the net work is equal to the change in the kinetic. Now we're going to start to break that work done by the different forces according to what kind of force we're dealing with. We talked about conservative forces already, right? So we said that conservative forces are special because they conserve energy, because they have a potential associated with the work done by those forces. I don't have to calculate the integral of these forces. I just need to know what's the potential energy difference, and that gives me that. So I'm going to break the net work into the net work done by the conservative forces, the nice ones, right? And the work done by the not so nice forces, the non-conservative forces. Okay? So this is the general situation, right? You could have a bunch of forces acting on an object, like me at this moment, right? Different forces acting on me when I move. So some of those forces might be conservative, right? And some of them might not be conservative. Not every force is going to be conservative. Not every force is going to have a work that is independent of the path. I'll give you an example in a minute. But for now, let me just say that there's some that are conservative, some that are not. The conservative forces are nice. Suppose that I have a bunch of them that are conservative. Force number 1 is conservative, force number 2 is conservative, and so on. The C means conservative, right? And I leave the non-conservative forces. I'm not doing anything with them right now. The conservative ones give me some nice result for the work. The work is always the negative of the change in the potential associated with that force. So I'm going to replace the work done by this force by this, the work done by the second one by this, and so forth and so on. We kind of did that already, but now we're trying to do it in a more general situation. So the conservative forces, I'm going to put all of the conservative forces stuff on one side of the equation, and I leave the non-conservatives on the right side. So the conservative part of the equation says that delta K plus the sum of those plus the change in the potential energy associated with each one should be equal to that, right? This stuff is the change in the mechanical energy. We define mechanical energy as the sum of kinetic plus all of the potential stuff that you have. Electric, gravitational, spring, anything that has a potential energy, we put it in there and we call it mechanical energy. So that equation is saying that the change in the mechanical energy of a system is only due to the non-conservative forces, because the conservative forces have a potential associated with them, and we take care of them with the potential energy. So if all of the forces acting on your system had been conservative, that means if they're all conservative, that means that there are no non-conservative forces, meaning we don't have any external forces pushing on the system. We don't have any dissipative forces like friction, air drag, and so on. So if everything is nice and conservative, then the change in the mechanical energy should be equal to 0. So that's the big statement about conservation of energy. If all your forces are conservative, then your mechanical energy is conserved. So we have come to the conclusion that whenever there is a change in the mechanical energy of the system, it has to be due to the presence of non-conservative forces. They will do work on your system, and when you add the work done by every non-conservative force, that stuff is what's going to change the mechanical energy of the system. The mechanical energy of the system will change. Okay? Now, what are these non-conservative forces? Let's start kind of discerning more about them. The non-conservative forces can be dissipative, but there can also be external forces. Okay? So this non-conservative stuff includes friction. When I'm pushing on an object, that includes the friction with the table, right? That would be a non-conservative force, a dissipative force. But it also, a non-conservative force would include the work done by external forces. Okay? Because when I put a force on an object, I change its mechanical energy, right? When I put a force on an object, I'm doing work by an external force, and that will change the mechanical energy. When I throw that ball that we were talking about, I was putting an external force. That external force did work, and that work changed the mechanical energy of the ball. Okay? So what I lumped on the right-hand side of the equation includes the external forces and includes friction, air drag, and other dissipative forces. So why are these, for example, friction or air drag, why do we call them non-conservative? Why are they not conservative? So let's look at a situation where we have a frictional force acting on a box. And we move this box from point 1 to point 2. So let's suppose that I want to push a crate on this room from point 1 to point 2. And I go along the straight line that connects 1 and 2. But what if I, instead of following this path, the yellow one, I took the crate and I pushed it around the room. I go over there, go around, and I finally bring it to point 2. Okay? Would you believe me if I tell you that the work done by friction, the work that I would have to do because I have to fight against friction, right, would be less if I follow the straight line than if I follow the curved one, right? That makes sense, right? So that means that the work done by this force, the dissipative force called kinetic friction, is path dependent. Depends on the path. Okay? So gravity was not that case at all. With gravity, it doesn't matter if I start from here and I bring it to that corner following the straight line, or if I move around, the force of gravity will do a work that it just depends on what's the difference in height between the initial and the final. That's a conservative force. Friction, non-conservative. It depends on the path. So the same thing is going to happen with air drag. These forces depend on, they're always opposite to the direction of motion. So these forces are called dissipative because they always decrease the mechanical energy. Whenever there's a dissipative force acting on the system, your mechanical energy goes down. That's what happens when I throw this thing on the table. I do some external work which increases the mechanical energy. This thing is left with some mechanical energy, but then there is a dissipative force acting on it, the friction with the table. So this object was left with some mechanical energy and it loses it, right? Until none of the mechanical energy is left. So the object has stopped. So what's the change in the mechanical energy that that object experienced? Let's say that there was a friction, so described by a coefficient of kinetic friction mu k, that you started with some initial kinetic, and that your final situation is you stopped, right? The mechanical energy went down from something to 0, but the question would be, did it just disappear? Gone? Or is it still somewhere? Joule was a British scientist. He was the first one to discover where did this mechanical energy go. One day he was observing how cannons were made. So back in the days, you would start with a solid chunk, right? And then you will use a drill to bore the hole, right? When you're doing that, the cannon and the drill bit get really hot. So you have to be pouring water constantly to be able to continue this operation of drilling. So Joule, thinking about that, thought that what was happening was that the mechanical energy of the drill was getting converted into another form of energy, thermal energy. It was getting the objects involved warmer. Okay? So once you state something like that, then you can extend the concept of conservation of energy and say that the energy is not just disappearing. The mechanical energy went down to 0, but it got transformed into a different kind of energy. It got transformed into thermal energy. Okay? And then you can do an experiment to prove if that's true. And the experiment will be measure the temperature of these surfaces after the block has stopped. Measure very carefully the difference in temperature between the block and the temperature of the block and the temperature of the table before and after. If you do that careful experiment, which Joule kind of did something similar, you would find that they're warmer. The temperature went up. That means they absorb energy. That energy came from somewhere. It came from the mechanical energy of the block. Now this might not be, I don't know if it might be hard or not to believe, but if I drop an object, nothing breakable here, if I drop an object on a table, the mechanical energy disappears. Once it hits the table, it's gone, right? But what I'm telling you is that the mechanical energy got stored in terms of thermal energy, and that this surface and that surface are warmer. But of course I touch this and you may have done this millions of times in your life, you never detected any difference in temperature, right? There is one, but it's not very, very evident. You can do a calculation, you calculate that temperature, and you'll find that, for example, for a 1 kilogram block of cement, if you drop it from 1 meter, so 3 feet, drop it on the table. After the cement hits the table, right, the increase in temperature of the cement will be about 0.015 Celsius. 0.015. So it is there, it's just small, and you don't normally feel it. But if you were to drop this cement, 100 times on top of this table, you would eventually feel that the surface of the cement and the table are getting warmer. Okay? This is the machine that Joule did to prove that. So it was just, he put water here in this container, a thermometer, and he had this thing that could spin, this paddle thing that could spin when the block went down. So this string is wrapped around this axis, right? And it goes to this block. He holds the block in position, and then he let it go, measure that distance, right? So that tells you how much potential energy this block lost, right? And then you can equate, and then you can measure how much did the temperature of the water go up. Okay? And indeed, the temperature of the water went up because the potential energy that the block lost went into thermal energy of the water. So he found the connection between heat, thermal stuff, and just plain energy. Because before him, people talked about calories as being an amount of heat that you need to warm up objects. Nobody had thought that you could warm up something by doing work on it, by mechanical means, right? So before him, calorie was something that related to heat, and energy was something else, right? He was the first one to say it's the same thing. We're talking about energy at the end of the day. Heat is the same as energy, and 1 calorie of heat is the same as, he did it from his measurements, he deduced that it was 4,186 joules. And now you know the joule where it's coming from. That's his last name. Before him, calorie had been defined as the amount of heat necessary to increase the temperature of 1 kilogram of water by 1 degree Celsius. So how much energy you need to do that? You need 4,186 joules.
Is that a lot?
That's a lot. If you think about the energy of a block, of a 1 kilogram block falling from some height, what height are we talking about? If it's a 1 kilogram times 9.8, that's about 10 times the height should be 4,186. So we're talking about 420 meters. So think of a 1 kilogram cement block falling from 1,200 feet. That energy of the impact, that would be used, that energy would only raise the temperature of 1 kilogram of water by 1 centigrade. Okay, so that is a lot of energy. Calories was used in food, right? The food labeling is in terms of these calories. So when a soda says that the soda has 100 calories, that's the same as saying that that soda contains an amount of energy equal to 418,000 joules. 418,000 joules. Okay, I already told you how much is this in terms of the height of a block of cement, right? Multiply that by 100. That's the energy of one soda that you drink. That's how much energy it has. So where did the energy go when that object dropped on the table and stopped? It went into thermal energy. Okay, now what's thermal energy? When you rub two surfaces together, surfaces are always going to be very rough. If you go to the microscopic level, there's going to be a lot of roughness between the two surfaces. So they're going to stick together. When you're rubbing something, those peaks are hitting other peaks and rubbing against them. And you can think of what's happening here the same as if you took a hair comb and then you put your finger and you ran your finger along the comb. So the teeth of the comb, what happens with them when you push them? You deflect them, and then when your finger passes, they come back and they oscillate and they make sound, right? So that energy of the sound is coming from the rubbing, the mechanical energy that I'm putting with my finger. So by doing that and transferring mechanical energy into oscillation of these hairs in the comb, right? So at the microscopic level, that's exactly what's happening. The big surface is rubbing on the other surface, and all these things are rubbing against each other and leaving each other excited, vibrating. That is thermal energy. That's increasing the temperature of the surfaces that are rubbing against each other, because the temperature is a measure of how fast the molecules are vibrating. The faster they're vibrating, the higher the temperature. So if you do something to an object and you leave the molecules vibrating faster, that means you increase the temperature of the object. So friction has that property. It's always going to increase the temperature of the two objects that are rubbing against each other. That's why people warm their hands like this, right? You're using friction to increase the temperature of the skin. So if what's happening is that the thermal energy of the system is increasing, then I could say that, let me look at the energy of the block and the table together. Okay? Because for that system, if I include the mechanical energy and I include the thermal energy, I can say that energy is going to be conserved. Right? Because what I would say is that the mechanical energy as the block is rubbing on the table is going to go down, but at the same time I know Joule told me that this is going to go up. Okay? So I can expect that if this goes down by 10 joules, this might go up by 10 joules. Right? That's exactly what happens. So you can use, if that is your new system, you're including the table in your calculations. The table is no longer an external actor here putting forces on the block. If the table is part of your system, you can say that the initial energy is equal to the final energy. That what you lost in kinetic energy, you gained it in thermal energy, right? That delta K plus delta thermal energy should be equal to 0. Therefore, if you lose kinetic energy, which you did, you would gain thermal energy. The objects will be warmer than before. That's what that equation is saying. You will gain thermal energy if you lose kinetic energy. How much thermal energy would you gain depends on how much kinetic energy you lost. If you started with this much kinetic energy, right, what you lost was that much, right? So you increase in thermal energy would be 1/2 of mvi squared. That's by how much the kinetic energy dropped. So your thermal energy is going to go up by that much, 1/2 of mvi squared. Now the reason why you dropped that, the kinetic energy dropped, was because there was friction, right? So I can connect friction in this equation. I can replace the initial velocity, right? One step back. Where is this part coming from? Vi squared should be equal to 2a times delta s. Where did I get that from? Kinematics, right? V final squared is equal to Vi squared plus this thing. But V final is 0. I stopped, right? So V final is 0, so you get Vi squared minus 2 times a delta s is equal to 0. So that Vi squared is this, right? That's the acceleration that the block felt because of what force? What force is accelerating that block? Well, gravity is acting in the vertical direction, right? The force that is slowing down this guy in the horizontal direction will be friction, right? So that acceleration is due to friction. So I'm going to replace ma with the force that is responsible for that acceleration, the force of friction. And I need to multiply by delta s. So the increase in thermal energy is due to friction times delta s, right? Notice that that's the negative of the work done by friction, because friction is doing negative work here. The force of friction is to the left. The block is moving to the right. Okay? So this number is the negative of the force of friction, of the work done by friction, because the work done by friction should be minus Fk delta s. Okay? So what I just did here tells you that the thermal energy increase if there is friction. By how much does it increase? It increases by force of friction, kinetic, multiplied by delta s. So whenever you have friction acting on your problem, this is how much that friction is going to increase the thermal energy of the system. Now in this situation, we have a car that is starting with some initial velocity equals 0, and the car is going to accelerate and reach some final velocity. So my question is, well, we know that the kinetic energy is increasing. There is no changes in potential energy. So, and we've been saying that energy is conserved, right? So where did that energy come from? Started with 0 kinetic, it ends up with some kinetic energy, 1/2 of the mass times the velocity of the car squared. Where did that energy come from? Fuel. If the car had no fuel, if the car had not been burning fuel, what would happen? It wouldn't move. It would still be there, right? So that energy came from fuel. So how do I incorporate that into conservation of energy? The fact that the energy of the fuel got converted into another form of energy, in this case kinetic. So what I'll say is that I have to incorporate the internal energy of the car. So there is internal energy stored in the material that makes up things. So there is an internal energy stored in the molecular bonds between atoms. And of course, there is also internal energy stored in the nucleus of the atoms. That's a lot of internal energy stored there. It's not easy to get to it, right? But there's a lot of it in there. So this one's a little easier to get to it because that one involves combining substances where the combination of those substances can end up breaking some of those bonds, and you might end up with less energy than you had at the beginning. So that energy is given off in terms of heat, kinetic energy of the molecules, and so on, which is what happens when you burn gasoline. You mix in the gasoline with oxygen. The combination of those two substances leaves CO2 and other substances which have less energy than the gasoline and the oxygen separate. So the deficit in energy is given in terms of temperature, right? So those things, there is kinetic energy of the molecules. They want to expand. They push the piston. The piston pushes on different parts of the car, which end up making the wheels turn, right? So all that energy, kinetic energy, came from internal energy. In this particular case, burning something is chemical energy. It didn't come from the nucleus. It came from the molecular bonds of the gasoline. So I'm try to give you the complete picture of conservation of energy in any situation. So that would be the mechanical energy is part of the picture. If things are moving, if they have potential energies, that is mechanical energy. But they also have energy in the molecules, right? Thermal energy is the kinetic energy and potential energy of the molecules that make up the object. So that's your thermal energy part. Then there is internal energy of the bonds between the molecules, internal energy in the nucleus of the atoms. So the change in all of this stuff, when you add the changes, they should be equal to the external work done on the system. If somebody's pushing on that car, then the car doesn't need gasoline, right? The change in the kinetic energy of that car would be due to the pushing force. So those changes, when you add them, that should be equal to the external work done. But there is an additional thing here that we haven't talked about at all here, which is the possibility that your system might be warmed up. That there will be, for example, a flame, an object that has a higher temperature that you put in contact with the object that you're talking about. That heat is given a letter Q, and when we talk about the first law and second law of thermodynamics, that will be there. So that's another possibility, right?